Imagine an absolutely stationary, massive planet. If you launch an interstellar probe directly toward its center, you can use the celestial body's gravity to continuously accelerate the probe, saving fuel and extending its range. But sooner or later, the probe will crash straight into the planet, making any follow-up exploration impossible. So you think of having the probe fly by at close range from the side of the celestial body. This avoids a direct collision. However, as it flies away, the planet's gravity pulls it backward, sharply reducing its speed. When it finally escapes the gravitational influence, its outgoing speed is exactly equal to its incoming speed. In other words, only the direction of its velocity has changed, not its magnitude. This process fully obeys the law of energy conservation, but it ignores the planet's orbital velocity. Then the clever you thinks, what if we take Jupiter, with an orbital speed of 13 kilometers per second, and make the probe's trajectory intersect Jupiter's orbit? After entering Jupiter's gravitational sphere, Jupiter's gravity acts like an invisible hand, dragging the probe to move in sync with the direction of Jupiter's orbit, effectively giving the probe an acceleration equal to Jupiter's orbital speed. When the probe leaves Jupiter, it is like tossing a ball out of a car window. The ball already carries the car's speed the moment it leaves your hand. In this way, you can achieve acceleration without consuming a large amount of fuel. But this plan still requires precise calculation. First, you identify a closest approach of 270 kilometers from Jupiter, where Jupiter's escape velocity is 30 kilometers per second. As long as the probe's speed exceeds the escape velocity, it will not be captured. So you design the probe to be launched from Earth at Earth's second cosmic velocity, 11.2 kilometers per second, ensuring it escapes Earth's gravity. Then, by leveraging Earth's orbital speed of 30 kilometers per second, the probe gains an initial velocity of 41.2 kilometers per second. Given that the distance from Earth to Jupiter is over 600 million kilometers, the probe's kinetic energy is continuously drained by the Sun's gravity. Suppose by the time it reaches Jupiter, its speed has dropped back to 11.2 kilometers per second. The probe then enters from behind Jupiter's orbital direction at an angle of 63 degrees. From the Sun's perspective, the probe's velocity can be broken down into two components: 5 kilometers per second in the direction of Jupiter's orbit and 10 kilometers per second perpendicular to it. If we switch to Jupiter's perspective, Jupiter considers itself stationary while its actual orbital speed is 13 kilometers per second. The probe's velocity in the forward direction then becomes 513 equals 8 kilometers per second, meaning the probe has a backward speed of 8 kilometers per second relative to Jupiter, while the perpendicular component remains 10 kilometers per second. Combining these two components gives a speed of 12.8 kilometers per second relative to Jupiter, headed backward at an angle of 128. During the encounter, Jupiter's gravity continuously pulls the probe closer and simultaneously bends its trajectory. By the time it reaches the closest approach of 270 kilometers, the probe's speed, boosted by Jupiter's gravity, has reached 33 kilometers per second, just above the 30 kilometers per second escape velocity, ensuring it won't be captured. After leaving Jupiter's gravitational sphere of influence, the probe's speed relative to Jupiter remains 12.8 kilometers per second, but its direction has been deflected to an angle of 16.5 degrees relative to the orbital direction. Now, if we break this velocity down again, we get a forward component of 10.7 kilometers per second and a perpendicular component of 7 kilometers per second. From Jupiter's perspective, the probe's entry and exit speeds are unchanged, but if we switch back to the Sun's frame, we must add Jupiter's orbital speed to the probe's forward component. 10.7 plus 13 equals 23.7 kilometers per second, while the perpendicular component stays at 7 kilometers per second. Combining these once more, the probe's final speed becomes 24.72 kilometers per second. From 11.2 to 24.72, with just one Jupiter and a string of numbers, you have achieved interstellar acceleration without burning fuel. Congratulations, you've just invented the gravitational slingshot effect. The famous Voyager 2, launched from Earth in 1977, used successive gravity assists from Jupiter, Saturn, Uranus, and Neptune to accelerate and ultimately fly out of the solar system toward the sea of stars. Of course, you could also replace the probe with Earth fitted with thrusters, and thus you have successfully conceived the Wandering Earth project. The universe never holds back its power. It simply waits for you to calculate the precise angle, ride the momentum, and push humanity's footprints, step by step, into deep space.